you have the recording of all the sessions, and try to upload these recordings also along with the notes, so that you can hear the recordings and understand it once again as your revision. Okay, so this is our total process design and detail engineering course that we will be covering. The program duration will be about 100 to 120 hours. Communication language English, of course. You have some other details, and I will first give you a complete program agenda overview, and then we will start with our first module. So the first module that we will be talking about is process design introduction, engineering and introduction. So this is where I think many of you already expressed an expectation that you want to understand the role of process engineer in the entire EPC life cycle of the project. What exactly a process engineer does, what is his responsibilities, what is the use of the role or activities done by process engineer in the overall project execution, who are the other engineers he interacts with, what exactly deliverables that process engineer receives from them, and what deliverables process engineer issues to them, and those downstream engineers, what do they use these deliverables for. Okay, so we will be discussing the role of process engineer here, the workflow chart in the EPC and process design deliverables that are generated. We will be discussing this next. Then we will have introduction to basic engineering package and front-end engineering design. So here we start with the complete life cycle of an EPC project. And the first stage in this is basic engineering package generation. And the next stage will be front-end engineering design. So we will see what are the typical activities that a process engineer performs in basic engineering package generation, and then downstream front-end engineering design activities. After these two activities, we roll over to the EPC phase of the project. So in the next part, we will discuss what are going to be the EPC activities for a process engineer, which deliverables he generates, issues them to whom, what tools that a process engineer uses for generating these particular deliverables, and how the downstream engineers will use these deliverables for their other engineering activities and procurement and construction activities. Then we will have a very short summary of oil and gas industry. And because in your chemical engineering you might have studied this in short, but may have forgotten certain things, so we will take a brief overview of what is meant by upstream industry, which are the units which are involved in the upstream industry, midstream industry, downstream industry, then the typical feeds and products from each and every unit. So we will go through basically what is meant by say oil and gas and water separation, what is meant by NGL fractionation, what is meant by NG liquefaction, what is meant by crude oil processing, that is a crude distillation unit, what happens over there, what products come out of that. Then the secondary processing units in the refineries such as DHDS, DHT, FCC, coker, what is exactly happening in those units, what products, what feeds are required for processing them, and what products are generated from them. And then downstream we go to the petrochemical industry, which is polymer generation or a paraxylene industry, aromatic industry, urea ammonia, that is a fertilizer industry. So we just take an input output overview of the entire upstream, midstream and downstream industries. So this could be useful down the line, because any process engineer, although engineering activities that he performs are typically same in all types of industries, but the technology will vary, and depending on technologies there may be some specific activities or more important activities that a process engineer will need to perform. And therefore we need to have some kind of a knowledge about which feeds are required for which type of industry, which products are generated, what is peculiar operating conditions, etc. for these industries. Of course, you can get a wealth of knowledge from outside internet as well as many other sources, about the process description, typical process flow diagrams for these types of industries, but we will take a general overview over here. So next we roll on to the second module, that is process engineering design basis. So the design basis is one of the very initial starting phase of the activities for process engineering, because this is the foundation on which the entire process engineering will be built upon. So generally there are two types of process engineering design basis done. So part A and part B. This is typical EIL terminology that I am using, and various consultancies use different names for that, and we will of course discuss those names also there, what is meant by that. Then we will see what is the typical contents of process engineering design basis in part A and part B. We will have an example, and then we'll have some discussion on material selection and design pressure, design temperature conditions. This is a part of the process engineering design basis. So going forward, in this particular modules that I have planned, what we are going to do is we are actually going to take a practical small size of a plant, and we are going to have actual design of the various process engineering activities of that particular plant. And in that process you will be introduced to a step-by-step approach, how a process engineer proceeds from the initial conceptual phase of the plant towards, let's say, simulation, heat material balance, then process flow diagram generation, then converting the process flow diagram into PNIDs, hydraulic calculations, equipment data sheet calculations, or equipment sizing calculations I should say, then equipment data sheets, PNID generation, cause and effect diagram, that is the instrumentation and logic, control narrative and control philosophies, safety studies like HAZOP, SIL. So how a process engineer will sequentially perform these activities, we will take a typical plant example to be designed, and with that example we will step by step go in performing these activities. So it will help you to get a complete chronological sequence of activities. Okay. So the third module, as I told you, that we will be taking a typical example of let's say I am talking about a depropanizer unit, which is a small unit where our objective will be, let's say, to fractionate a mixture of LPG, which is propane and mixed butanes. LPG is basically propane, N-butane and isobutane mixture. So we'll take a small example that we have a fractionation column for distillation of propane in the overhead and mixed butanes in the bottom. So we will start with the design basis generation of that particular plant, then the design basis part B, then we will start with process simulation for that plant. So we will be using DWSim as an open source process simulator, which is of course free, so anybody can download it and use it, and it is more or less reasonably accurate because we are not going to actually build any plant. So the small amount of inaccuracies in that free simulator, it doesn't matter for us, but it will be very good starting point for you to get introduced to process simulations, how they are performed, how modeling is done, how thermodynamics is selected, how convergence is achieved in the process simulator, what are the important specifications to be provided during the performing the simulations, and then next onwards will be heat and material balance to generation from process simulations, and converting the process simulation into process flow diagrams. Okay, so in the theory part of process simulations we will cover the various process simulators. So as we know, there is Pro2, Aspen HYSYS, Aspen Plus, ProTreat, ProMax, so many simulators that are available. So what is the advantage, disadvantage of any simulator? What is the basic components of a simulator? Then the most important part, the appropriate selection of thermophysical property package. So what is the importance of having the most correct selection of thermophysical property package, and how to decide which package to be selected? So when I see our interview people, they say, okay, I know simulation, I am expert in simulation. Then when I ask them, okay, what is your basis of selection of thermophysical property package? Almost 99 out of 100 people answer me that, okay, I just select Peng-Robinson or Redlich-Kong SRK as a thermophysical property package. But this is not an appropriate answer. Everything cannot be simulated by the SRK or Peng-Robinson thermo. So we will see the basis of selection of thermophysical property packages. For what system, what package should be selected, and what is the reason for selecting that particular thermophysical property package. Then we will go with the actual simulation of a distillation column. So as I explained you that we are going to take the example of the depropanizer column, and we will start with the, let's say, feed surge vessel, then a pump, then discharge side, the control valve, preheating, and distillation column itself, product cooling, everything we will simulate in the DWSim and generate a final simulation. Of course, that columns optimization also we will do, but we will probably do it towards the end of our last second last module, that is distillation column module, because by that time you would have understood the theoretical concepts of optimizing the distillation column. So in the beginning we will only perform basic process simulation for the distillation column to generate the heat and material balance. Okay, so any doubts so far, anyone having? Okay, great. So next we roll over to the fourth module, that is hydraulic calculations. So once we have performed heat and material balance for the plant, so next stage will be the appropriate line sizing, because for generating the PNIDs the line sizing is necessary. So we will look at the different types or activities that we perform under hydraulic calculations. The part 1 of the module will be optimum line sizing for liquids, gases, as well as two-phase. Of course, two-phase we will not focus too much upon because it is a high-end technical expertise that is required. So probably as entry-level process engineers, people will not expect you to have, you know, thorough knowledge in that. And of course, there are specialized people who can do this type of two-phase hydraulics. In the second part, we will discuss on pumps and control valves. So here somebody was telling me that you want to understand the equipment design. So we will look at the pumps, what is meant by, let's say, centrifugal pump performance curve, how it looks like, what is meant by system curve, what is meant by the duty point, how the control valves construction is there, how we select different types of control valves, what are the specifications for the control valves, how to let's say specify different design conditions for the control valve, which will help us generate the instrument process data sheet for the control valve. So we will be doing a pump and control valve sessions or technical theoretical knowledge together. Okay, so we'll have all these covered. So and the next one will be, of course, what is pump minimum circulation flow. It is another very important aspects of pump design. And we will look at the control valve sizing, basically for single phase design only, because anyway the control valve exact or accurate design is more of a instrument vendor matter than a process engineer matter. But process engineer role will be to provide the correct specifications for sizing of this control valve by the instrument vendor. And then in the next part we will do or perform actual hydraulic calculations for the pumping system. So in this case we will see a particular pump, let's say the plant that we are designing, the depropanizer column or a fractionation. So it will have a feed pump as well as a reflux pump. So we will be looking at the actual hydraulic calculations for these two pumps. So that will help you understand how the line sizing is done optimally, the control valve sizing is done optimally, or control valve specifications are provided, and the pump design is done optimally. So here in this case, the feed pump will be like a single destination, because the feed pump will only deliver the feed to the distillation column. So it will be a problem with one destination. And the reflux pump, because it will be typically common for reflux as well as the distillate product being sent to the storage. So this becomes a multiple destination problem for centrifugal pump hydraulics. So in one two particular examples, we will cover two different types of systems which are designed for pump hydraulics. Okay. Then the next module, and this module we have specifically introduced this time. In our previous courses it was not there. So what we envisaged is that the process safeguarding and process control, these are very important aspects of process engineers design. So therefore we expect that our process engineers who are getting trained from our lectures should have a very good, or at least fundamental knowledge about process safeguarding. So we will look at what is meant by the layers of protection, that is the control layer and emergency shutdown layer, and the next layer, that is the safety valve layer. So what are the typical signals like digital and analog signals, hardwired versus soft link? So some of you who are coming from operations background, you already might be knowing about these things, but some of you who are freshly graduated may be having lesser knowledge about it. So we'll explain that. Then what are the different types of controls, that is on off control, PID control, and the DCS control system. Again, the guys from operation background will be well aware about the DCS control systems. Then interlocks, cause and effects, logic diagrams, emergency shutdown. So we will explain a bit of this, and again you will be familiar, people coming from operations background will be familiar with this, but we will have an overview of this. And then something that you may not have been much familiar with is the safety studies. So any plant necessarily requires some safety studies to be done to gain a confidence on the design that is being performed. So we will look at what is meant by hazard, that is hazards identification, then the HAZOP, that is hazards and operability studies. We will look at what is meant by safety integrity level or SIL. So you might have heard of these terminologies called SIL 1, SIL 2, SIL 3, SIL 4, and you may not be fully aware of what it means by SIL 1 or SIL 2, when to go for SIL 2, when to go for SIL 3. Some overview we will be having for this. And then of course the dispersion studies, that means whatever open vents we are having to atmosphere, so we need to perform the dispersion studies. So we'll have a short discussion on that. And quantitative risk assessment. So what is meant by quantitative risk assessment, what is the outcome of that, and what is the process engineer's role in all these studies. The next module we will be covering is piping and instrumentation diagram. So this is one very important module wherein we see how we will convert the process flow diagram which we had generated earlier into PNI diagram. We will look at the legend sheet and symbologies, typical details which are to be shown on the PNID, how we show the instrumentation, control and emergency shutdown systems on the PNID. We will have discussion on SPPNIDs, what is nowadays has become an industry-wide trend. So what is meant by a smart PNID, and what is the difference between a smart PNID and an ordinary AutoCAD kind of PNID. How we generate smart plant PNIDs, what inputs are required for that, and how the downstream engineering disciplines get benefited from using smart plant PNIDs over ordinary PNIDs. And we will actually see the example of the PNID of the depropanizer column that we are designing. So now you can see that starting from design basis, how we have proceeded into generating every deliverable corresponding to the example of the plant that we are talking about. The next module will be process safety valve, another important module where process engineer has a big role to play. So the part 1 of this module will be safety valve terminologies. So here we will get ourselves introduced to what is meant by say design pressure, maximum allowable working pressure, set pressure of the safety valve, what is meant by blow down, what is meant by simmer, what is meant by overpressure, under pressure, what are the different scenarios for safety valve design. All these design considerations we will look at. The second part of this module will discuss about the safety valves design. So here we will introduce ourselves to different types of safety valves. So what is meant by conventional safety valve, balance below safety valve, and pilot type safety valve? What are the constructional features and differences between them? And which safety valve do we select at for which application? We will see that. We will also see the criteria or the design aspects about how to calculate the orifice sizing of the safety valve. And in the part 3, which is a big actually module or sub module I should say, here we look at actual safety valve design, wherein we go in a very sequential manner. That means first we start with the system to be protected by the safety valve, how to identify the limits of that system, how to locate the or decide the location of the safety valve, how to identify the scenarios that are associated with that particular system overpressure. So when we talk about API 520, 521, it gives us a numerous number of scenarios that might be applicable, and we need to apply our process engineering judgment to decide that this particular safety valve will be required to cater to which all scenarios. So those scenarios may be like general power failure or cooling water failure or tube rupture for the heat exchanger tubes, or a fire scenario, control valve wide open scenario, gas flow by or gas breakthrough scenario. So we will look at the explanation of all these scenarios and how typically the relief load, that is the flow rate to be relieved, is calculated for each of this scenario. So we'll give you some guidelines.
Sir,
Yes.
sir, in this you also include a PRV, na? The pressure relief valve.
Okay, so here the terminology what we are talking about is a pressure safety valve, but in the part 1, that is safety valve terminologies and design considerations, we will explain you what is meant by PRV, PSV, what is the difference between PRV and PSV, and which one is used for which particular application. So although the title mentions as pressure safety valve, the pressure relief valve will
Okay.
also be part of this particular module.
Okay, sir. Okay.
Okay. So in this part 1 itself,
Okay,
we
sir.
will have both the terminologies, the relief valve, safety valve and safety relief valve, and what is the difference between them and which one is preferred under what circumstances.
Okay, sir.
Next we go to the vessel sizing. So here we have the single phase vessel, that means the liquid only vessel typically, then two phase separator sizing, vapor liquid separator, three phase separator sizing, that is VLLE, vapor liquid liquid separator, where two liquid phases, that is let's say typically water and a hydrocarbon phase, are immiscible from each other. So what are the design principles for the two phase and three phase separator design? What are the equations and how those are utilized in, let's say, Excel sheets or typical softwares which are used for the separator design. Then we will see the actual calculation sheets in Excel for two phase separator. For three phase separator, we will only go through the design principles, but not do the actual design, because there will be some proprietary softwares with each and every company that will be used for the three phase separator design. But we will look at all the underlying principles that are used for three phase separator design. Then we'll see the preparation of data sheets for the vessels and actual examples. So again we will use maybe a typical distillation column overhead reflux drum for the depropanizer unit we are talking about, or feed surge vessel we will be using for design of vessel sizing and vessel data sheets. The ninth module is heat exchanger design, in which we will have discuss on types of heat exchangers, what is mean by TEMA configuration, that is Tubular Exchanger Manufacturers Association, what are different TEMA configurations. So with respect to TEMA A, B, C and K and various configurations we will study. What are the advantages and disadvantages of each type of TEMA configuration, which TEMA configuration is preferred for what application. Okay, so this is required or important for generating the proper process data sheet for the heat exchanger. So selection of heat exchanger, shell and tube heat exchanger type will be discussed in detail. Then we will discuss the design parameters for shell and tube exchanger. So starting from the exchanger orientation, so horizontal exchanger or vertical exchanger, which how orientation is selected. Then approach temperatures between hot side and cold side. What should be the approach temperature and why those particular temperatures should be selected. What is the effect of using or choosing tighter approach temperatures? What is the effect of choosing wider approach temperatures? Okay, with respect to the capital cost and operating cost both. Then we will look at typical fouling factors which are to be used for different applications. Another important aspect of heat exchanger design, that is fluid allocation, wherein we need to decide that out of the hot side and cold side fluid, which fluid should be allocated on tube side and which fluid should be allocated on shell side, and what are the criteria for such selection. For example, whether it is a fouling service or a non-fouling service, which one out of the two is a high pressure, high design pressure condition and which one is a low design pressure condition, then which one has a more temperature drop, as well as what type of TIMA configuration we are choosing. So depending on corrosiveness of the fluid, fouling nature of the fluid, so depending on the various aspects of the hot and cold side fluids, how we decide and make a judicial choice of the fluid allocation on shell and tube sides. Then the next one in the design aspect, that is baffle orientation. So horizontal baffle, vertical baffle, inclined baffle cut. What is meant by that? How to decide the percentage cut for the baffle and the baffle spacing? What is the effect of change of baffle cut and baffle spacing on the performance or thermal design of the heat exchanger? We will look at that. Next we see what is meant by LMTD correction factor or F factor. Why it is important, how to calculate it. I think this is something you might have learned during our heat transfer in chemical engineering, but we will again touch upon that, okay, because it is an important parameter in the thermal design of heat exchanger. And lastly, we will try to design a heat exchanger, but at the same time I can tell you that probably I am not a very high-end expert of heat exchanger designs, so we will give an attempt to designing of a heat exchanger. The last module or second last module here is the distillation column design. Now we come back to the optimization of the depropanizer column, which we had done during process simulation. So here we have again two parts of this module. The first one is the process design of distillation column and second one is a hydraulic design of distillation column. So under first one, that is process design, we will revisit McApthil method, which we had learnt in our chemical engineering. What is meant by minimum number of stages, minimum reflux ratio, what is concept of optimum reflux. This is a new concept which is normally not covered in the chemical engineering courses, okay, but is very important in the actual simulation of the distillation column. Then how to determine the actual number of stages for optimum reflux, how to optimize the feed tray location and the reboiler and condenser duties. Then what is meant by tray efficiencies, because normally the simulations that we perform or the McApthil methods that we apply them on just a moment. We apply them on theoretical stages, but real column will obviously have an efficiency lesser than 100%. So what are the different types of efficiencies and how to convert the theoretical stages that we use for simulation into actual number of trays in a physical column. Okay. So some of you who come from operating background would be obviously knowing that there may be hundreds of trays in a distillation column, but the fractionation performance that those trays give will not be 100%. That means you will not be able to achieve 100 theoretical stages performance from those stages. So we will take an overview of the various types of efficiencies and how they are applied to convert the theoretical stages into real trays which are used for the design of the column. Then we will see the selection of internals for the column, that means the tray column versus pack column. Which one should be chosen for which application, what is the advantage and disadvantage. The second part of the column design is hydraulic design. So here we will learn what is the different column terminologies in hydraulic calculation. So here we will learn what is mean by jet flood, downcomer flood, what is mean by weeping and entrainment, what is the typical design and operation zone for the distillation column, and then we will see actual example of the same depropanizer column which we have already performed the process simulation. So the same column we will do the hydraulic design. So the objective of the hydraulic design will be to arrive at the diameter of the column, the tray spacing, the number of passes. Okay, so one pass or two pass design, the downcomer width, all the mechanical details which are required for generation of the process data sheet for the distillation column. So kg tower example that we will take will be able to design the whole column and provide the complete data sheet to the mechanical engineers. So in the last module we will talk about the compressors. So what are the different types of compressors, that is centrifugal compressor, reciprocating compressor, screw compressors, and on what criteria the different types of compressors are selected for different applications. We will look at the centrifugal pump, centrifugal compressor performance curves, and the most popular topic what everyone knows maybe from operation background, of course, those who have seen and operated the compressors, is what is meant by surge of the compressor, what is meant by the stonewall operation of the compressor. Those are the two limits, one on the extreme left and other on the extreme right side of the compressor design or operation. What is meant by anti-surge control system? So some of you, maybe a DHT plant who has operated, somebody having an experience will be knowing what is anti-surge control system. So why it is important to avoid the surging of the compressor, and how the anti-surge control system will be able to avoid the surging phenomena in the compressor's operation. Then we will look at the various compressor capacity control methods. So the suction throttling method and RPM variation method. So these are the 2-3 different types of capacity controls. The next activity process engineer performs is settle out pressure calculation, where it is important that these calculations have their importance in designing the suction side design pressure of the compressor system. So what is meant by settle out, under what circumstances it happens, and let's say when the compressor trips, so the pressures will equalize from discharge to suction by opening of the anti-surge valve. So how to calculate this eventual pressure, because the suction side, which is normally experiencing the low operating pressure under the normal operation of the compressor, it will suddenly experience a high pressure, and therefore the design pressure of the suction side has to be increased to handle this high pressure during the tripping phenomena of the compressor. So how to calculate this settle out pressure, we will be looking at that aspect. We will look at typical compressor PNID schemes. So for a reciprocating compressor, how the PNID looks like, what are the valving systems and control systems for the reciprocating compressor. Similarly for the centrifugal compressor and screw compressors, we will see the typical compressor PNID schemes. And we will look at multi-stage refrigeration systems and the role of intercoolers in the multi-stage compressors. So under what circumstances we need to split an overall compression, high compression ratio system into multiple number of stages, and how many stages we should choose, on what basis, whether we should provide the intercoolers or not. to optimize the power consumption as well as to limit the discharge temperature from the compressor stages. So we will look at these criteria for decision of multiple stages, how many number of stages, and intercooler requirement between the stages. And then we will have the final revision and closing session, wherein we will discuss about your overall doubts about whatever modules have been covered so far, and we will see the typical questions in a process engineering interview. So there will be a kind of a mock interview also finally. So we will talk on one-on-one level with you, those of you who are targeting some interviews, about how you will approach a particular interview. So this kind of gives you an overview or a glimpse of the various modules that we will be discussing and covering in the our overall course. Okay. So any